Last time we got introduced to the idea of optimization, which essentially is just you're trying to maximize or minimize a certain outcome. And our goal is to figure out how we can do that. Let's look at the question number 1, a very simple question. So we have a piece of a wire that's 25 centimeters, 100 centimeters long, and we need it to form a rectangle. Determine the dimensions of a rectangle with the maximum area. Okay. So let's say this is our rectangle. Should I use the straight line tool? Let's say this is our rectangle. We don't know what the length is. Let's say it's L. We don't know what the width is. Let's say it's W. You have 100 centimeters of wire to work with. What's the perimeter of this rectangle in terms of L and W?
2W plus 2L.
So we know the perimeter is 2W plus 2L. And what is the perimeter? Do we have a number for this? How much wiring do we have? That would be the perimeter.
100 centimeters.
So we have 100, right? Can we pull out anything here?
A 2.
A 2. So you can divide both sides by 2. You'll be left with W plus L, which will give you an equation. W is equals to 50 minus L. So there you go. That's equation number 1. That's not the answer, but that will help us find the answer. In terms of L and W, what is the area of this rectangle?
LW.
LW. Now we know what W is in terms of L, because right now we have 2 variables, very difficult to work with. Ideally, we only want to have 1 variable. So I'm going to do a quick substitution, replace the W with what it is. So this becomes L times 50 minus L, right? Like that.
Mm-hmm.
Open the bracket, what do you get?
50L minus L squared.
So I'm going to write it like this, negative L squared plus 50L. So that is our area function. So on the y-axis, we have our area. On the x-axis, we have our length. And this is what it looks like, negative L squared from 50L plus 50L. What are the x-intercepts for this? Because what it is essentially is a negative quadratic, right? We're trying to find what length gives us the maximum area. It's a negative quadratic. It's going to be opening downwards, which means if we can find the 2 x-intercepts, there's only one way of doing it, by the way. It looks something like this. If we can find the 2 x-intercepts, we can find the midpoint, and that'll give us the L value, which will give us the maximum area value. That's one way of doing this. You don't even have to know calculus to do this, honestly. So how do we find that vertex? It's very simple. We need to find the 2 x-intercepts. So set this equal to 0. Pull out an L. So you'll be left with negative L plus 50 equals 0. So what is L? What are the 2 x-intercepts? Either L is 0, right? Yeah?
Mm-hmm.
What's the other value of L? If you set this equal to 0, what do you get?
50.
50. Those are the 2 x-intercepts. So where's the midpoint?
25.
So L value of 25 would give us the maximum area. Now let's plug 25 in here. So that'll be negative 25 squared plus 50 times 25. And that gives me 625 centimeters squared. And there we go. That's the final answer. But this is the beauty of calculus. You don't need to know what it looks like. You don't have to do the x-intercept things. Here's how you find it. The maximum or minimum always happens at a turning point. So what you do is you want to find what the turning point is. Maybe I shouldn't have erased it, actually. Let me just keep the graph. I'll keep the graph. We just need to know where the turning point is. We know it's 25 because we cheated using the other method. But there's a very simple way of finding what that L value is. What's important about a turning point? What happens at the turning point?
The slope is 0.
The slope is 0. In other words, the first derivative, a prime, is 0 at that turning point. What's a prime? What's the derivative of this?
Negative 2L plus 50.
Yes, negative 2L plus 50. You solve this, you will get L as 25. And then you want to plug that back in here. That will give you the area as 625. So you don't have to graph it if you know that the first derivative is going to be 0. Okay?
Mm-hmm.
So this is a very simple problem. Here's a quick pro tip. Max area, maximum area will always be a square. So here L was 25. This is what our diagram looked like. This is 25. This is 25. 50 is left over. That means width is also must be 25. And this is a square. Area is maximized when you have a square shape, okay?
Mm-hmm.
Let's try this. So this is like netted area. This is your golf ball here. And you whack it into this area to practice your golf shots. What they have told us is that the volume of this, what do you see wrong about this statement right here?
Volume shouldn't be squared.
Volume shouldn't be squared. So I hope they mean the volume. We're going to pretend they mean the volume. So we're going to cube this. Yeah, I don't know how they got us. So probably a typo, most likely, unless we're missing something. No, definitely a typo. So we know the volume. So volume is 144 meters cubed. In terms of the letters defined by this shape, it's a, what is this? How would you describe this shape? Is it a sphere? Is it a pyramid?
No.
How would you describe it?
A rectangular prism.
Yeah, a rectangular prism if you look at it this way. You can say it's a square prism if you look at it this way. So it's a prism, it's a rectangular prism. What's the volume in terms of x and y?
It's x cubed.
It's not x cubed because it's a rectangular prism, right? So
Oh.
it's x squared y. Okay?
Mm-hmm.
Like that. I really don't want to deal with plus minuses, so I'm not gonna solve for x, I'm gonna solve for y. What's y?
It's 12.
Good try. No, it's not. It's 144 divided by x squared. It would have been 12 if the x squared wasn't there, but there's the x squared. So we don't know what the precise value for y is. And that is going to be our substituting term, okay? We have y. It's asking us for the amount of netting. Netting means what? This stuff, okay? This stuff. It goes here, goes here. It says it goes on every side except the front face. So 1, 2, and then this side here. Whatever the bottom one. No, the bottom also doesn't need it. So front doesn't need it, bottom doesn't need it. So we have 1 face, 2 face, The third hidden face here. Any more?
Back.
The back, yeah, exactly, the back. So there's 4 faces that we are interested in, and we're trying to minimize the netting. So what are we looking for? Volume, area, perimeter of these 4 faces.
The area.
The area, exactly. What's the area of this face?
XY.
XY. So that's 1 down. What's the area of this upper face?
X squared.
No, this one,
It's
X,
also XY.
it's also XY, yeah. What about this side face, this one?
It's also XY.
It's also XY. What about the back face?
That's X squared.
That's X squared. So there we go. This is our area function. Let's do our substitution because we have 2 variables. We don't like 2 variables. 144, sorry, x times 144 over x squared. I'm just gonna be smart here. This is 3xy plus x squared. Now I'm gonna do a substitution. I'm gonna call this 1. So we do 3 times x times what is y? It's 144 over x squared plus x squared. This cancels out with the squared. I can even take an LCD if I want. I am gonna do that because I don't like fractions. It's easier to deal with when you have LCD. What's 3 times 144? I want you to think of it like this, okay? 3 times 144 is 3 times 150 minus 6, right? Like that. What's 3 times 150?
It's 450.
Yeah, and then 3 times 6 is 18. What's 450 minus 18?
It's 432.
Yes. So if someone asks you to do 3 times 144, you don't want to be doing this. We'll give you the answer. It's not like it's not going to give you the answer, but you don't want to do it. You want to do it like this so you can do it in your head. All right, so that's our area function. We need to do what with it? We need to either maximize it or minimize. We need to minimize it. But honestly, for either approach, the idea is the same. You want to find the turning point, and there's only one way you can find the turning point. What do we do to A to find the turning point? Remember, the horizontal tangent there is going to be 0. The slope is going to be 0. So what do we do with A?
You set it to 0?
No, not A. The slope will be 0. So you set the slope of A to 0. What's the slope of A? The first derivative, A prime, okay? So you want to set A prime equal to 0. Here, let me show you what I mean by this. I don't know how to graph this. It's going to be a terrible graph. This one's going to be a terrible graph because you have an oblique asymptote, which involves long division, this and that. Boom, boom, boom. So I'm going to graph this. Graphing this is, like I said, it's not that easy. So this is what it ends up looking like, right? So what are we trying to find? We're trying to minimize. It says minimize. So are we looking for a minimum or a maximum?
A minimum.
Minimum. There's only one minimum. Notice what happens at the minimum. The slope, there's a turning point. The slope is going to be 0, right? That's going to be 0. So we need to find that point. So let's work on finding that point. We're going to set the first derivative equal to 0. Actually, how would you find the first derivative of this? Which technique would we use? Quotient rule, product rule?
Quotient rule.
Quotient rule, right? So here's what quotient rule says. This is F, this is G. Quotient rule says it's F prime G minus F G prime all over G squared. So let's do this. What's F prime? What's the derivative of the numerator?
3x squared.
3x squared, perfect. Times g, so it's going to become 3x cubed. Do you agree? 3x squared times x is 3x cubed. This is 3x squared, and g by itself is an x, so 3x cubed minus f by itself. So that's going to be 432 plus x cubed. What's the derivative of the denominator?
1.
1. So you multiply this by 1, nothing changes. All over the original square. There we go. That is our a prime. How do we solve this for 0? For x, sorry. It's equal to 0. How do we solve this for x? Try getting rid of the denominator. What happens if you multiply both sides by an x? What happens if you multiply both sides by the x squared in the denominator there? Does it disappear?
Yeah.
Yep, x squared gone. And now let's open that bracket. We can collect the like terms. It'll be 3x cubed minus x cubed minus 432 equals 0. 3x cubed minus x cubed, 2x cubed equals 432. Yeah.
Mm-hmm.
X cubed equals 216. 36 times 6 is 216. So x, so you can also think of it this way. X is the cube root of 216, x is 6. There we go. Which means y will be 144 over 36, which is 4. So x equals 6, y equals 4. Final answer. Did that make sense? So what we're doing is we're just using area volume formulas, taking the first derivative and solving for whatever the value, whatever the equation ends up being. It looks very difficult, right? Like here, this is a rational equation here, especially with the x squared. It looks tricky, but no, it's just a few steps. If you can see it, then you're good. Also, one more of these. Determine the area of the largest rectangle that can be inscribed in a right triangle if the legs adjacent to the right angle are 5 and 12 centimeters long. Not super sure what it means yet, but let's sketch it. Will give us a better idea. So we have a right angle triangle. This is 5 centimeters. This is 12 centimeters. And we need to fit a rectangle in here and maximize the area of that said rectangle. The two sides of the rectangle lie along the legs. What does that mean? I think it means something like this. So there you go, that's our rectangle. Let's call this L. Let's call this W, okay?
Mm-hmm.
Now what? What's the area? Hmm. What's the area of the rectangle right now?
LW.
LW. Can we take the derivative of this?
No.
Yeah, that we ideally you want to take the derivative of one thing, right? And then set it
Mhm.
equal to 0. So then what do we do? You want to start thinking of this in terms of the area of the rectangle. What is this side length going to be? -12 minus W. What is this side length up here?
L minus 5.
Let's do 5 minus L because L is less than 5. Let's do 5. You see what I mean? L
Mhm.
minus 5 would give you a negative number because from this diagram, L is much smaller than 5. Okay. Forget about the rectangles. Let's find the area of the big triangle. Area of the triangle. Base times height divided by 2. So that's 30 centimeters squared. So that's the area of this rectangle. What's the area of this? It's going to be in terms of letters. No? What's the base of this triangle? What's the base? This side.
W.
W. What's the height? This height right here. 5 minus L, right? Base times
Mhm.
height divided by 2. So that's the one triangle on the top. Plus this area right here. L times W, the rectangle in the middle. Plus, what's the area of this rectangle here?
L times 12 minus W over 2.
L times 12 minus W over 2 seems good. So when we add these three areas, what do we get? It's right here. 30. So when you add those three areas, it must add up to the area of the big triangle that we started off with. Yeah?
Mhm.
All right, now we need to solve this equation and either solve it for L or solve it for W. So let's see what that would look like. I'm going to take the LCD, which means the entire denominator is 2. So I just need to put a 2 here, multiply both sides by 2. That'll give me a 60 on the other side. All right, we're done with fractions. Now let's open the brackets. So this is going to be 5W minus 5L plus 2LW plus 12L minus LW, yeah,
Mhm.
equal to 0. LW minus LW is LW. Negative 5L plus 12L is 7L. 5W is, well, 5W. Equal to 60.
Shouldn't it have been 5W minus WL?
5W minus W. Here?
Yeah.
Yeah, that was wrong. It should have been 5W minus LW is what it should have been, right? Yeah.
Mhm.
So this gives us, what does it give us then? Are there any like terms? These two? Oh, sorry, no, not the W. We have LW, LW, LW. So, okay, yeah, this is easy now because LW minus LW is 2LW. 2LW, so right now we have negative 2LW and then we have positive 2LW. So they cancel out. See it?
Mhm.
From here it's easy. So W will be 60 minus 12L over 5. There we go. That's our substitution. We're very close. Now we're going to replace that LW, that W, with what we found from this substitution. So this will be L times W is 60 minus 12L over 5. 60 minus 12L over 5. Let's open the brackets. That gives me negative 12L squared plus 60L over 5. That is my area function, A function right now. How do I find the minimum or maximum when I have an equation? You find the what? First derivative.
derivative.
Yes. What you can do actually is before you find the first derivative, because I don't want to use a quotient rule, I'm going to split the denominators. Check this out so you don't have to use a quotient rule. Negative 12 over 5L squared plus 12L, like that. I just put the 5 here and here. I'm allowed to do this. Just distribute the denominator. Now let's find A prime. What's A prime? What's the derivative of this function that we have? It's very simple. Negative 24 over 5L, okay? Plus, what's the derivative of 12L? The letter disappears.
12.
It's 12. And what is the first derivative always equals to in optimization? 0, right? Because we're looking, we don't know what this looks like, but we know there's going to be a turning point somewhere. So we set this equal to 0, and let's solve for L. My L looks terrible. So it's negative 12 over 5L equals negative 12. Negative 12 goes into itself once and goes into negative 24 twice. So we have 2L is 5, therefore L is 2.5. Boom, that's the question. Make sense?
Mhm.
Super difficult question? I don't think it's super difficult. It's just that you need to, this part is easy, is super easy. Like anyone can do this. The harder part is what do we sub in? So for that one, you have to think of, sometimes you have to think of it outside the box. For me, my approach was, I know the area of the big triangle. Maybe if I split it up into 3 different chunks, I can get something that I can sub it in here for. So that's kind of like the mindset you want to use to solve optimization problems. It gets way more difficult than this, but this is a good question. I'm not even going to bother with this because that's kind of hard to see. Let's see. There's no AK questions here, which is terrible. There's this, discuss the result of maximizing the area of a rectangle given a fixed parameter. The answer is that it has to be a square. A square always maximizes the area. It's the only quadrilateral that maximizes the area when you're given a parameter, if you want a 4-sided diagram. Also got a little bit of difficult question. So again, for all of these, I'm going to sketch because it's easy to sketch. That's just a quadratic. For that quadratic, where are the x-intercepts? How do I go about graphing this? Do we know the x-intercepts? Do we know the y-intercepts? What about the y-intercept? No? Is it opening up or down? It's a quadratic, yeah? It's a quadratic.
It's opening up.
It's opening up. It's not that difficult. Here, let me show you. To find the x-intercepts, you just set it equal to 0. Like that. Square root both sides. Go to 0. So where's the x-intercept? At 3, right?
Mm-hmm.
Now remember, the square means something. We talked about this when we did polynomials. This is an order 2 polynomial. This x-intercept is an order 2 x-intercept. Order 2 means there's a squared here. What does order 2 x-intercept mean? Is it going to pass or is it going to be a turning point? Order 2 means there's going to be a turning point, okay? So at 3, we have the vertex right here. The y-intercept here is 9. It's very easy to see. Y-intercept is when x is 0. Remember, x-intercept is when y is 0, and y-intercept is when x is 0. Like that, you'll get a 9. So the y-intercept is 9. So let's say 2, 4. It's somewhere up there. Okay, whatever. It's somewhere up there. And then it's going to come down. And then it's going to go right back up. That's a terrible sketch. Let me do better. A straight line tool doesn't. I wish there was a curve tool here. There's not, which is like my bane here. So it comes here and then goes up like that. There we go. Boom. That's our quadratic. Now, where's our second point? Negative 3, 3. Negative 3, 1, 2, 3, 3, 1, 2, 3. This is our point right here. Minimal distance. Minimal distance. Now this keyword is important. Let's say there's a line here, okay? Let's say there's a line. Minimal distance. What's the angle there if the distance were to be minimized?
90.
Did we talk about this? Perpendicular distance is always the shortest distance. Here, let me show you. Here's A, here's B, right? Here's a point, here's a point. Let's say this is going this way, this is going this way. The shortest distance will always be perpendicular, okay?
Mm-hmm.
So we know the angle there is going to be 90 degrees. What's the question? It says the distance. Okay, we need to find the distance itself. We could find the distance if we know this point. See that?
Mm-hmm.
How do we find that point? How does this line relate to this curve? What's happening here? Let's say this point is xy, okay? Let's say that point is xy. There's a name for this point where two things meet. What is that called? Point of intersection, yeah?
Mm-hmm.
POI, point of intersection. This point right now is negative 3, 3. From this point to this point, what's the rise? What's the slope of this line? It'll be here. Look at this. I know it's a little bit difficult because we're not talking pure numbers here. And I'm not kidding with you. Eventually, when you keep doing math, you'll never see a number. Or you'll never see a number more than 1 digit. Everything is going to be in terms of letters. So the slope of this line, okay, look at this. Rise is going to be y minus 3. This point, the y value here minus this point. What's going to be the run?
X plus 3.
X plus 3. So that's our slope. Okay? I'm going to call this M. So let's come up with the equation for this line. That is going to be y equals mx plus b. So it'll be y minus 3 over x plus 3 times x plus b. That's the equation of that line. Cool?
Mhm.
So when we set this line, this is the line. When we set this line equals to x minus 3. Actually, I'm going to use different letters because now I'm confusing myself. There's multiple x's, multiple y's. Let's call that a comma b. Nothing changes really. It's only the notation that changes. I'm going to call that point AB so we don't have multiple a's and b's. So that means the rise will be b minus 3. The run will be a plus 3. And also the y-intercept, let's call it something else. Let's call the y-intercept k as well. Like that. What is the solution to this problem? What are we expecting to get at as the final answer? Where does this line meet this curve? At which point? It's right here.
AB.
AB, right? So what's the x value at their point of intersection? It's A, right?
Mm-hmm.
What's the y value at their point of intersection? B.
It's B.
How do you find the distance between 2 points? The distance between 2 points. Forget about this question. Once you know how to find the distance between those 2 points, you can just put it in the formula here. Let's say you have 0.11, and let's say you have a 0.34. We can even sketch it, because you need to know how to do this to answer that question. Let's say that's 0.11. This is 0.34. What is the distance between these 2 points is the question. How do we find it? No? Here's the easiest way to do it. Turn it into a triangle. Into a right-angled triangle. What's the height? We're going from 1 to 4. What's the height?
3.
What's the run?
2.
2. How do we find this distance? We know these two side lengths. Pythagoras.
Pythagoras theorem.
Exactly, this is going to be root 13. So distance between 2 points, right? Distance between 2 points, just turn it into a triangle. It looked difficult last time because we had like AB here, and we had, I think, negative 3, 3, right? The distance between these 2 points, look at this. You can turn this into a triangle. So B minus 3 is the height, agree?
Mm-hmm.
Squared, because we're using Pythagoras theorem, plus the run is A plus 3, or A minus minus 3, A plus 3 squared, like that. And then you square root this, and there you go. That's the distance formula. So what we had there, we could have substituted for either A or B here. So the entire thing will be either in terms of A or in terms of B. And once you have that, you take the first derivative, you set it equal to 0, you square both sides, and it's easy from there, okay? So remember, distance between 2 points, turn it into a
Triangle.
triangle, exactly. Okay, let's move away from shapes. Let's do some real life problems. It says optimization problems in economics and science. What are you taking in grade 11? Are you taking economics or science or business, or how does it work?
We don't really have like other courses like economics, so it's just like the different sciences.
Okay, which one's your favorite?
I like chemistry.
Chemistry? Okay, chemistry is fun, yeah. What about organic chemistry? You know what that is?
I think we're doing that next year.
Okay, yeah. Once you get into that, maybe you won't like chemistry as much. But no, chemistry is good. Yeah, chemistry is good. The only issue with chemistry is that you can get a degree in it, right? But you probably are gonna need a master's to get like a decent job. You can definitely get into like any lab stuff with a bachelor's, but you definitely need to do more work in chemistry. Same thing with economics as well, with how competitive the markets are these days. Anyways, let's look at this question. There's a train. Capacity is 2,000 people. And it brings you from, let's say, point A to point B somewhere. Small city, large city. The cost to ride the train is $7 per person. So we're given a cost, $7 per person. Market research shows that 40 fewer people would ride the train for each 10 cents increase in the fare, and 40 more people would ride the train for 10-cent decrease in the fare. If the capacity of the train is 2,600 passengers and carrying fewer than 1,600 passengers means costs exceed revenue, what fare should the railway charge? Okay, cool. So this is the question. We don't need the ABs. The max passengers you can carry is 2,600. The min passengers you can carry is 1,600. Yeah? How many passengers is it carrying right now?
2,000.
2,000. So let's say passengers, and then we're also gonna say cost. So right now it's carrying 2,000 passengers. What's the cost?
$7.
$7. So that is our initial case. Let's do this statement. 40 fewer people. Okay, 40 fewer people. No, actually, let's first talk about the money. Let's say the fare goes up by 10 cents once. What is the new fare?
$7.10.
So it'll be 7 plus 0.1, yeah, times 1. This is 1 increase of the fare. How many passengers do we get? 2,000 minus 40 times 1, right? See that? So let me do the math right now. So right now, this is what? 14 with 3 zeros. So this is the revenue, is 14,000. Now let's do this. That's going to be 1960. We're not going to do this by hand. I'm just showing you the idea. Times 7.1. Well, right now, the revenue is 13,916. So that was case number 1. Let's do case number 2, the opposite. What would that look like? It's the next statement. How would you phrase it like I did here?
You would do plus 40 times 1.
Plus, yes. What about on the other side?
7 minus 0.10 times 1.
The goal is to maximize the revenue, yeah? And remember that times 1 means the fare went up by 1. It doesn't have to go up just by 10 cents. It can go up by 10, but it can only go up in increments of 10 cents. So it can be 7 plus 70, 0.77 plus $2. It can only go up in terms of 10 cents increments. So here's the trick to this question. Let X be, okay, the number of fare increases or decreases. Basically, this is X, this is X. So we have 2 conditions. We raise the price. What is our revenue function in terms of X? It has to do with this. Revenue is always passenger time cost. How many passengers?
2,000.
Minus what? 40 what? X. Because this can be 40 times 2, 40 times 3, 40 times 4, right? What's the cost then? It's this part here. 7 plus 0.1 times what? X, okay?
Mm-hmm.
So if you raise the price, depending on how many times you raise it, this is your revenue. What kind of a function are we looking at? Is it a sine function, log function, exponential, quadratic? What is it? You want to look at the power of x's. When you multiply, when you open them, what's the final power you get?
2.
2. So it's a quadratic, right?
Mm-hmm.
It's opening down because negative 40x squared. When you would open this, you would get a quadratic. How do we find the maximum of a quadratic? Find the vertex, yeah?
Mm-hmm.
Find the vertex. But you don't have to, that's grade 10 stuff. So if you want to do it using calculus, what you do is you open the brackets, set the first derivative equal to 0, and solve for x. That's the approach I'm going to use. So this will be 14,000 plus 200x. I'm just opening the brackets. 200x minus 280x minus 4x squared. I just open the brackets. That's my revenue function. I need to find the maximum, so I take the derivative of this. What's going to be the derivative of this? It's pretty simple. It'll be 200. 14,000 disappears. It'll be 200 minus 280. I guess we can even write this as negative 80x here to make our lives easier. Negative 80x. Negative 80x. So the derivative of this would be negative 80 minus what?
Minus 8x.
Minus 8x. We set this equal to 0, right?
Mm-hmm.
So negative 8x is 80. So x is minus 10. So that's the answer. To maximize the revenue, you have to decrease. Minus 10 here means you have to decrease the price. So let's go back up here. So we have to go with this one. How many times was it? 10 times. So your new fare will be 7 times 0.1 times 10. That will be $6. And your passengers will be 2,000 plus 40 times what? 40x, right? X is 10. 10. So how many passengers do we get? 2,000. Because when you decrease the fare, the passengers go up, right? Does that make sense intuitively?
Mm-hmm.
The lower the price, the more people you want in. That's how Uber and Airbnb, these companies, startup companies, they boom, they have a big booming phase in the beginning because everything is cheap because they operate on a loss. So 2,000 plus 40 times 10 is 2,400. When you do this times 6, boom times boom, the new revenue, you want to pay attention to what it was initially. Before it was 14,000, but now the new revenue after you decrease the price 10 times, 10 cents each. There we go. Your revenue increased. Even though you lowered the prices, your revenue, right? That's what's important. Revenue means the money that the company makes. The revenue went up even when they reduced the prices. And that is one of the real life applications of an optimization problem, something like this. Let's say you work as a transport engineer or something, you would be crunching these numbers. The only issue with this is that obviously it's not going to be consistent. Just because you drop it by $1 doesn't mean you would get 40 people in every train, 40 extra people in every train. So that's a limitation. But you can counteract that limitation by collecting data. most transit services these days, they know exactly how many people tap, right? To go into a train station. I don't know how it works there. Where are you? In Saskatchewan?
Edmonton.
Edmonton now, right? So you have to tap something to get into a train station, or even on a bus. And when you get in, you have to tap something, right?
Mm-hmm.
They have this data. Every transit company has this data. They know exactly how many people take the transit. So they can kind of make an average recommendation using the data that they have. Cool?
Mm-hmm.
And that's what they got as well, 14,400. You need to decrease the fare. That would be the answer. All right, for now, let's call it there for now. This was a tricky class. I will see you tomorrow.
Okay, thank you.
Bye-bye.